Alright, this is going to be our second video in our electric flux and Gauss's law series, and in this video we're going to look at a number of examples. Actually, the whole video is going to be devoted to looking at several examples of calculating electric flux through a variety of different surfaces. So we're going to do the three examples from the textbook. I'm not going to go all the way up to the point where I substitute in numbers, but I'll kind of just review them. We're going to talk about some stuff that they don't talk about in the textbook a little bit, and then we're going to do a fourth example that isn't from the textbook, where we're going to deal with a non-uniform electric field, because all the examples they did in the textbook did deal with, well, I guess the third example didn't really deal with a uniform electric field, but because of symmetries we're able to sort of simplify the problem. But let's start off. So let's start off by keeping in mind the three equations that we went over last video. So our equation for electric flux, where we don't really have to worry about integration. Then the one where we are integrating because our electric field is not necessarily uniform. And then let's remember that we now think of areas not as scalars but as vectors, with the magnitude of the scalar we used to think of, but pointing in a direction normal to the surface. And this is something that I didn't mention in the last video, but we also want to note that for any closed surface, our normal vector will always point outward. Okay, so I didn't mention this last video, but I probably should have. So imagine, I don't have much space here, but I'll draw it here. Imagine that we have a closed surface, right? So some sort of a surface that encloses some region of space here. We'll make this one like a cube. All the normal vectors here are going to point outward. So our normal vector here is going to point outward, outward, and outward here. Okay, so these would all be let's say normal unit vectors. But if we had some other surface that is not a closed surface, but just a surface, let's say we have this disk from the first example we're going to be looking at, then we really have to specify which way our normal vector points. Either it's going to point this way, or it could point back this way, right? There's no inside or outside, so we really need to specify which way the normal vector is going to point. Otherwise, we're going to be off by a minus sign, right? And so with these tools in mind, let's take a look at some of these examples. So we'll start off by looking at example 22.1 from the textbook here. And so I guess I'll read out the problem, even though we're not really going to use these numbers. I'm just going to think of this angle here as phi, so we don't really care about the 30 degrees. But you could take it a step further than I'm going to here. Just sub in the numbers and see that you get the answers from the textbook. So we're going to start off. We have a disk of radius 0.1 meters. It's oriented with its normal vector, normal unit vector, pointing at 30 degrees to the uniform electric field. Right. So we see that here. We're given the magnitude of the electric field, and then it mentions that since this is not a closed surface, there's no concept of inside or outside. We need to specify the direction of our normal vector, and they do that for us, right? So in part A, we want to calculate the electric flux through the disk, I guess in its present configuration, and then we want to see what the flux through the disk is if it's perpendicular to E, and so forth. So I'm sort of just going to do this in one shot here. We're just going to calculate it for any angle phi, and then we could just substitute in whatever angle we want for phi and just get our answer, right? So let's keep this picture in mind. This is our uniform electric field. We have a disk. It's either offset or not by some angle phi. This phi could be 0, this phi could be 90 degrees or whatever. Or it could be more than 90 degrees, and then our normal vector is pointing in the opposite direction of the electric field, and we would just pick up a minus sign for that. But let's take a look at this here. So I'm going to do a solution my way. The textbook does it a very similar way, but they take it all the way to substituting in numbers, so you guys could see how that would work out. But so first of all, let's note here that because our electric field is uniform, we don't need to be concerned about a changing electric field in different regions of the disk. So we don't need to do any integration here, right? We can jump straight to our first equation here, our equation 1, and kind of solve the problem. So we're going to have our electric flux is equal to, oops, that should be the top of the E. It's going to be equal to E dot A. And let's remember that E dot A really is saying that we have E dotted into the magnitude A pointing in the direction of our normal, right? And so if we do that, this is going to end up looking something like this, right? We could rewrite this in these terms, where phi is the angle that we have labeled on our diagram here, right? And this is just simplifying this dot product. We just factor out the magnitude A, and we factor out the magnitude of our electric field, and we just do the dot product of the direction of the electric field dotted into the direction of our normal vector here, so unit vectors, and we end up with this expression that we see here, right? So at this point we would just substitute in the numbers, and the textbook does this. We just sub in the numbers for E and for A and for whatever phi we want, and we get whatever answer we're looking for, right? But what the textbook doesn't look at is could we have solved this by integration if we wanted to? Let's say this electric field wasn't uniform, or let's say we simply forgot this equation and we wanted to solve this by integration. Could we do that, right? And the answer is yes, we can do that, and we're going to find that we get the same answer. Let's start off from the expression that we have above. This is our expression for the electric flux, right? And so we're going to be integrating over our surface. So the way I'll do that is I'll just write the integral over the surface with this s as a subscript here, and this integral can turn into a double integral or whatever, depending on what we're doing. In this case, it'll be a double integral because we're integrating over a 2D surface, right? And so this will look something like this, dotted into dA, which we talked about. And so much like we saw in the disk example that I did in our meetings, where we're integrating the disk example from last section, I should say. So we're integrating over the whole disk, and so if we want to integrate over the whole disk, our DAs, the scalar DA, is going to end up being S ds d theta, right? And theta here is not the same as phi. When we're talking about integrating over the disk, we're thinking about our disk. If we're looking at it sort of head on, this is the center of the disk, right? And we want to integrate over all these tiny little chunks. Imagine that this would be here. Let me label this. So this would be theta, and this little tiny piece of angle in here, this would be d theta. And this would be, let's say we were doing some chunk out here. Let's say this is the chunk that we're interested in. This would be our S. And this tiny little thickness of chunk, this would be ds. And that's probably very, very hard to read. This would be ds, okay? So we're integrating over all these tiny little sections of our disk, and this is what our dA becomes. We're going to be integrating over S and over theta, right? Except that our dA here, our dA is really a vector dA, and what that means it's just dA in the n hat direction, okay? And so we can rewrite this. This is going to be S ds d theta n hat, okay? And because our electric field here is uniform, we don't have to worry about some sort of algebraic expression for our electric field. It has no dependence on any of these variables. It's the same everywhere. So we're just gonna keep it in the form of E. So let's say we wanted to rewrite this integral. I'm going to rewrite this here, and so we're going to end up with, we need to do the double integral. We're going to be integrating from 0 out to r. This is going to be our S integral, and from 0 to 2 pi in the theta direction, right? And what are we integrating? We're integrating E dot S ds d theta in the n hat direction, okay? And so again, neither our E nor our n hat depend on S or theta. So both of those can flow straight through the integral, and we end up with something that looks like this. Okay, so we're going to have our electric field dotted into our normal vector. Okay, and this is going to be times the integral from 0 to r of s ds, and the integral from 0 to 2 pi of d theta. Okay, and now we just have to solve those integrals, and we're pretty much at the end of the problem here. So let's start off. We'll start off by looking at these terms. So our dot product here, E dot n, or n hat I should say, is just going to end up being E, right? This is just the magnitude of E. Why is this? Well, because we know that E and n hat point in the same direction. N hat has a magnitude of 1. So I mean we could think of it like this, right? It'll be E times the magnitude 1 of our normal vector, right? Because this is a unit vector, right? And because we're doing this dot product, it's going to end up having a cos phi, right? And so depending on what this angle phi that we've looked at above ends up being, we're going to account for that here. This is just a simplification of the dot product. We pull out both of the magnitudes. Magnitude of E vector is E, magnitude of n hat is n, and this cos theta accounts for the theta that we see in the drawing above, right? So that's that part. If we look at, maybe I'll do this just so we know where these terms come from. So this part here, this integral s ds here from 0 to r, if we do that integral, this definite integral, we're going to end up with a term that looks like this: 1/2 s squared from 0 to r. Okay, and that's this term up here, right? And if we do the final integral on the end here, the integral d theta from 0 to 2 pi, we're going to end up with theta from 0 to 2 pi, right? And so simplifying these, let me simplify them down here. We're going to end up with E cos phi. From this term here, we're going to substitute in r, and if we substitute in 0, we get nothing, so we're going to end up with 1/2 r squared, and from here we're just going to end up with a 2 pi. Okay, 2 pi. These cancel, right? And I'm going to rearrange these slightly. We're going to end up with with something that looks like this: E pi r squared cos phi. And what is pi r squared when we're looking at a disk? Well, this is just our area, right? And so we end up with E a cos phi. And I believe that's the way we wrote it above here, right? So this was our answer, just not doing the integration. If we had chosen to do the integration, we end up with the same answer here. And again, we can substitute in for any value of E. The electric field could change, and we could find whatever that value of E is, whatever our A is, which we know is just pi r squared, so we could change the radius of our disk, and we can change our angle phi, the sort of facing of that disk, and get whatever answers we want, right? So that was 21, no, what is it, 22.1, sorry, from the text. All right, let's take a look at the next example from the text. This is 22.2, and in this one we are looking at a cube sitting in a uniform electric field again, and then we rotate the cube slightly and take a look at it again. So we need to find, well, I'm going to read the problem in a second here, but basically what we're going to do is we need to find the electric flux, or actually, let me pause the video and save this before I lose this PDF. One sec. Okay, so like I was saying, we need to find the electric flux through each face of this cube. Right, so we're going to be looking at the electric flux through each face of the cube, and what are we kind of expecting to find, right? We're expecting to find no net electric flux here because there is no enclosed net charge, right? So let's remember, we haven't really talked about Gauss's law yet, but we're kind of on our way to Gauss's law, and what this is basically telling us is that if there is no enclosed net charge, there should be no net flux through the surface, okay? And let's see if we find that. again, our electric field here is uniform, and because it's uniform, we don't need to use any integration here. Could we use integration? Yes, we could, like we did in the previous example. We didn't need to, but we could. We could break up each of these surfaces into a ton of little tiles, and integrate over each surface separately. And if we had a non-uniform electric field, that's in fact what we would have to do. And then sum up over all those different faces and see that we would actually end up back at zero because we're not enclosing any net charge here, right? So let's get sort of right down to the problem and see what we get here. So in this first case, the face of the cube, which has a normal unit vector n1, is facing with its normal unit vector opposing the electric field, and 2 points in the direction of the electric field, and then we have N3, N4, N5, and N6 are pointing perpendicular to the uniform electric field. Okay, so that's for part A. We'll start off with part A here. Okay, so for part A, let's just start adding things up, right? So we're going to start off from our electric flux, right? We remember our expression for the electric flux is this, which we can rewrite in this way. I'll use theta here this time. And so this, let's remember, this theta that we're using, this is the angle, or maybe it'd be less confusing. Yeah, okay, so I'm going to use, well, what do they use? They use theta for the other angle. Okay, so I'm going to use phi here. And so let's remember that this phi is the angle between our electric field and our area vector, depending on which face we're looking at, right? So let's start off, let's look at face 1. And maybe before I even do this, we're going to find that our total electric flux, the sum of all the electric flux going through this closed surface is going to be the sum of all the faces. So we want to sum over all these faces. I'm gonna let I run here. So it's going to be the sum over all the EI is going to give us back our total, right? So this is really going to end up being the electric flux through the first face plus the electric flux through the second face plus all the way up to the sixth face, right? And so let's take a look at what's going on with the first face. Which one's the first face? It is the one that's pointing in the opposite direction to the electric field. So we have the flux E1, we're going to call it, and we're going to have E. What's the area? Well, this is a cube, right? And the problem tells us this is a cube of side length of side length L, right? And I didn't bother to read this, but basically we've talked about the whole problem now, so I don't really need to at this point. But we have our cube of side length L, so the area of any one of those faces is just going to be L squared. So we're going to have EL squared, and this is the angle between that area vector and the electric field. In this case, it's going to be 180 degrees, right? Because they're pointing in opposite directions. So that's going to end up giving us a minus sign, right? This is just minus 1. And so we end up with minus EL squared. For phase 2, the flux through phase 2 is going to look like this. We're going to have EL squared again. And this time, the electric field and the area vector point in the same direction. So this is going to be 0 degrees. And so we end up with EL squared. And then for each of these ones, for phase 3, equals phase 4, phase 5, and equals phase 6. This is going to be equal to 0. And why is this? Well, these are all equal to 0 because in this case, our electric field is perpendicular to our area vector, and this means that we're taking the cosine of 90 degrees, and the cosine of 90 degrees is 0. So all those go to 0, right? And then so using this sum here that we talked about, we want to see what the net electric flux through the entire closed surface is. We just add all these up, so it's going to be minus EL squared plus EL squared plus 0 4 times or whatever, and it's just going to end up giving us 0, right? So that's great. We expect it to find 0 because we have no enclosed net charge, and that's what we do find for part A, right? In part B, what are we doing? In part B, we are rotating the cube slightly about our z-axis here. We can kind of imagine that we have some x, y, and z-axis here, right? So we have like a right-handed coordinate system, and our z-axis points in the direction of our normal vector 5. And so we've rotated this thing slightly by some angle theta. So this is now 90 minus theta, and this is now theta here, okay? And so now we want to, again, examine what's going to happen. What are we expecting? We're expecting, again, to find no net flux through the closed surface because there is no net enclosed charge, right? And so we're going to see if that's what happens when we've rotated this thing. How do we rotate it? Counterclockwise. Yeah, we rotated this thing slightly counterclockwise. So we rotated it like this, counterclockwise by theta. Okay. So we rotated it that way. Let's see if that changes anything. So for part B, again, we need to sum up all of the contributions from the 6 different sides. We can see again that although more sides are going to contribute now, to 2 of the sides that were 90 degrees to the electric field aren't anymore. Our sides 5 and 6 still are, so those are going to give us no contribution, but 1 through 4 will give us some contribution. So let's see what those are. So we're going to have the electric flux through our first surface is going to be equal to EL squared, and now we're taking the cosine of 180 minus theta. And if that isn't clear, kind of take a look at the diagram above and kind of think about that a little bit. It's going to end up being 180 minus theta because of the way that we rotated things. But there's a trig identity. We can kind of rewrite this. So I'm just going to rewrite it here. This is going to end up being minus EL squared cos theta, right? And we just pick up that minus sign because of this 180 degrees. Okay, so that's just the cos theta here plus this minus sign that I've pulled out. What's happening for the second surface, our flux E2? That's going to be, well, that's just going to be EL squared cos theta. So take a look at the diagram here. We talked about the first one, right? So we have the 180 degrees minus this tiny little theta rotation, right? Because we're going we're kind of turning back toward the N1 hat facing toward this. So it's 180 minus that theta. For our N2, we just have some rotation of theta, right? So we've turned theta degrees that way. And let's see what we have for the other two. For our third face, we're going to have EL squared, and this is going to be cos 90 degrees plus theta. Okay, and again, if you want to kind of look at the image before, I'll let you pause it and take a look there, but this is basically what we're going to end up with. We can simplify this again because this 90 degrees can be pulled out as a minus sign, so we're going to end up with minus EL squared cos theta. And if any of these sort of trig identities don't make sense to you, just think about it for a little bit. Think about a unit circle and what cos means on the unit circle, right? So think about a unit circle where this is our x and this is our y, and we have some angle theta in here, and we're rotating this thing. What is cos giving us? Well, cos is giving us this distance always, right? It's the adjacent side to our angle. And if you think about adding or subtracting 180 degrees from this, you're going to see that all these identities kind of make sense, right? And so finally we have our flux through our fourth face. If we look at that one, that's going to end up being EL squared cos 90 minus theta in this case, okay? And this will simplify down to EL squared cos theta. And again, we talked about how through phase 5, and through face 6. This is going to be 0, right? Because again, these the normal vectors are going to be perpendicular to the electric field, so we're going to get no contribution there. If we sum all these up, I probably don't have to write it out here. We can see that this one cancels with this one cancels with this one, and again we find a net electric flux through our closed surface of 0, as expected, because we found it before, and we've only rotated this thing, and we know that there is no enclosed net charge, and so we expect no net flux through the closed surface. Okay, let me just pause this one more time to save this again. Okay, so now let's take a look at example 22.3 from the textbook, and this is the electric flux due to a point charge through a sphere here. And so this one's kind of interesting because our surface isn't flat, and our electric field is not uniform, right? This is not pointing in the same direction everywhere. It changes at every point. And so in principle, we would need to actually do this integral over the full spherical shell, right? But we're going to see that because of the symmetry of the problem here, we can simplify this a great deal, and the integral really becomes trivial. Well, as we'll see here in a second. So I'm not going to bother reading the question. Basically, we have a point charge surrounded by our closed spherical shell here, and we want to find the electric flux through the sphere. Okay, and in this case, we do have some enclosed charge, right? We have a charge of Q enclosed here, so we do expect to see some flux through our closed surface, right? Maybe I didn't need to leave all this space here, but we will use it anyway. Okay, so let's get started. We know that we're going to have to use an integral here, right? Because our surface is not flat and our electric field is not uniform. We know we're going to have to use this expression here. Okay. Except that because of the symmetry of the problem, let's look at the diagram again. If we look at the symmetry of the problem, we can see that yes, E is changing everywhere. At every different point, E is different. But at every point, our normal to the surface, our n hat, is going to change, right? At this point, our n hat to the surface points like this. At this point, it points like this, right? So this is E, this is n hat, and it just so happens that because of the symmetry of the problem, everywhere we have E, and maybe I shouldn't, I'll just leave it here. E is parallel to n hat at every point on our spherical shell here that we're interested in calculating over. So what does this mean? Well, this means that we can simplify our dot product a great deal, right? So we started off with this, but it turns out that the dot product is just going to end up giving us magnitudes, right? And so because of symmetry, this is going to end up being this, right? And this is much easier for us to deal with, especially in this case, because now that we've done this, our E, although it's not uniform, it isn't dependent on what part of what little tile on the sphere we're looking at, right? Because it's the same at every point, right? Because we're always a distance r away, and we're always pointing in the same direction as our normal vector. Our E has no dependence on the stuff that we need to integrate over, and I'm not going to get over. We'll sort of get into the details of how to integrate over this spherical shell for right now. But this means that we can factor out this E. It's not going to change as we integrate over dA, and we end up with this, right? But this integral, the integral of dA, when we're integrating over this spherical shell, well, what is this? This is really just the surface area of our sphere. So we don't really need to do this integral. We just know that the surface area, well, maybe we know, or we should know, that the surface area of a sphere is just going to be 4 pi r squared. Okay, and this is equal to A, which is equal to 4 pi r squared. This is just the surface area of our spherical closed surface. Okay, and so that's great. We've kind of simplified what could have been a messy integral down to just a simple substitution here, and so we end up with E 4 pi r squared. And in this case, I'll take it a little bit further. We know we can write what the expression for E is, because we know that or maybe I should make some notes here. This is the area of our shell, and E here is for a point charge. And we know that for a point charge, we can just write the electric field for a point charge as Q 4 pi epsilon naught over r squared, right? And so this is our E, and we still have this 4 pi r squared, r squared over here. A lot of this stuff cancels out. We can cancel out the 4 pi here, the r cancels, and we're left with Q over epsilon naught, okay? And this is interesting. This kind of demonstrates that it doesn't really matter how large our enclosing surface is if the same amount of charge, well, we have to be careful. If the same amount of point charge, let's say we could change this Q to have a different magnitude, right? But as long as it was a point charge centered at the center of our circle here, we would find the same electric flux. Remember, this is our electric flux. Through that enclosing surface, right? There is no r dependence here, so it doesn't matter what we make r. We can make the sphere as large or as small as we want, as long as the symmetries remain, right? We're going to have the same result, and we can scale Q up as much as we like, and it still stays the same, except that now we'll have a larger Q, right? So this would be our answer for the flux through our spherical closed surface around our point charge, which is at the center of that spherical shell, right? So we do have to kind of be careful. If this wasn't right in the center, if the point charge was off to the side, this would become a little more complicated, right? Because we couldn't just argue that the normal vector points in the same direction as the electric field everywhere necessarily. And if we kind of lost the symmetry, if we had additional charges inside or some sort of charge distribution with a different shape, we'll see kind of what happens later on. But with what we know so far, we can't just make that assumption, right? So here we were able to use a symmetry, and we were able to clean things up, and that's great, right? So that's the answer to this third one. I was kind of disappointed that the textbook didn't do one with a non-uniform electric field, so we have one here. We'll take a look at this one. So in this example, we're looking at a non-uniform electric field defined by this expression here. So at different points x, y, and z, our electric field is a function of x, y, and z. So at different points in x, y, and z, it's going to have a different magnitude, right? And it'll point in different directions, right? We're interested in this electric field and this surface, a surface defined by this expression here, right? And so what is this really saying here? Well, maybe I'll draw the surface here to make it easier. So what is the surface telling us? Well, this is telling us that we're looking at a surface that's located at y equals 3. It extends from x equals 0, not inclusively, from x equals 0, from x equals 0 to x equals 2, and from z equals 0 to z equals 2. So let's draw this surface just so we have it sort of in our minds what it looks like. So I'm going to draw our coordinate system here as best as I can. Right-handed coordinate system. So we have our x, our y, and our z here. And if we imagine, maybe I'll draw this a little larger. Okay, so if we imagine counting out 3 along in this direction, so this is like y equals 3, we're going to have a surface sitting here. So at y equals 3, because it's telling us here y equals 3, we have a surface that extends from x equals 0, right? This is x equals 0 out to x equals 2, right? So this is some length 2. Doesn't matter what the units are. Could be whatever. And we're going to have our z coordinate here also extending from z equals 0 to z equals 2, right? So we have some surface here, okay? And we're going to end up breaking this surface up into a bunch of tiny little tiles and integrating over that surface. So imagine this surface sitting out in space here, and we also have this electric field, which is a function of x, y, and z. So it's not uniform; it changes everywhere. So we need to be really careful how we handle this, right? We need to integrate over our full area from x equals 0 to x equals 2, and from z equals 0 to z equals 2. Over our electric field and actually calculate what the flux through the surface is. So let's go back to the problem, give it one more quick read through now that we have an idea for what the surface is, and then solve the problem. Okay, so consider a non-uniform electric field defined by this expression we have here, and a surface defined by the expression that we have here. We want to assume that A points in the positive j hat direction, and we want to find the electric flux through S. Okay, and this last piece of information that A points in the positive j hat direction was necessary because it's not a closed surface, and so the normal to the surface could either point in the negative j hat, and maybe I'll draw them in here. This would be like k hat, j hat, and I hat, and so this normal vector could either point in the negative j hat or the positive j hat direction. It's telling us that the area vector points in the positive, well, I guess these will be dA's, but in the positive j hat direction, right? So let's write down our expression. Do I have space here? I do. Okay, so we know that we're going to have to integrate to find this. So this is going to be our electric flux through the surface. This is going to be equal to the integral over, and this is going to be over the surface, right? So this is our surface S. It's going to be the integral over the surface of E dot dA. And so what do we need to integrate over here? Well, what is our dA? Well, our dA is going to be dx dy, right? We need to integrate over, or no, sorry, it's not going to be dy because we're going in the z direction here. It's going to be dx dz. Okay, so we need to be careful. We're going from 0 to 2 in the x direction, and we're going from 0 to 2 in the z direction, and so we're integrating over dx and dz, and our area vector, our infinitesimal area vector, is going to be dx dz j hat, right? Because we know it points in the positive j hat direction. We're told what E is. We're told what E is up here. So let's just copy both of these down. We have our vector dA and we have our E, so let's copy them in here. I'm going to turn this into a double integral because integrating over the surface means that we're going to have to integrate from 0 to 2 in the x direction, from 0 to 2 in the z direction, and then we're going to have our E. So I'm just copying in the expression from above, which I have on a paper here, which is y squared I hat plus z squared j hat plus x squared k hat. And obviously this electric field could be anything. We just chose this this electric field at random, kind of. And then this is our dA. We have dx dz in the positive j hat direction. Let's start off by doing the dot product. So we're still going to have our integrals here. And if we do the dot product, only the j hats are going to remain, so we're going to end up with well, only the magnitudes from the j hats will remain, so we're going to end up with z squared, dx dz, right? And now we can address those integrals. I'm kind of running out of space. It should be fine here. So the dx will just flow through the z integral. We're going to end up with 0 to 2 dx, 0 to 2 z squared dz, right? And if we do those integrals, what do we end up with? Well, this is just going to give us 2. This is going to give us, using the power rule, or the kind of inverse power rule, we're going to end up with 1/3 z to the third from 0 to 2. And if we do that, we are going to find that we have 2 from the first integral. And if we sub in a 2, we're going to end up with 2 to the third over 3, which is going to be 8/3. And if we multiply that through, we're going to find 16 over 3. Okay, and this with no units here, this is our electric flux. Okay. All right, so that would be the answer for this one, and we will move on to looking at Gauss's law in the next video.